and try to give you an idea of what's important things to know. Okay. All right. So when we look at glycolysis, okay, so we're going to be looking at it in terms of four major sub-processes that occur in glycolysis, and I'll sort of highlight each of these. In the first set of reactions, the first steps, you get addition of phosphate groups. Okay, so in order to make this reaction go, you actually have to add some components to that glucose molecule in order to get it to react. Then you split the sugar. That's actually where you get the name glycolysis. Lysis means to split. And then after you split that sugar into smaller molecules, each of those can be used to generate two things, make two things. One is reducing power. Okay. This is where we go from NAD to NADH. And reducing power is a way of storing energy. And then second, you can make energy directly in the form of ATP. So that's that's the energy currency that we talked about. Okay, and we'll take a quick look at that as well. All right. Okay. So now going through these, first of all, we need to add phosphate groups, and the reason why we do that is that raises the energy level of the molecule. Okay, so in order to break that molecule down, we actually have to raise the energy level of that molecule. That's kind of like if you wanted to do damage to this. Right, one way to do damage to this is if I can lift this way up high in the air, right, and drop it. Okay, right. That increases the amount of energy to break this. That's what we're trying to do in some sense with glucose. We add the phosphate groups to raise that energy level, right? So that in a way activates the glucose for breakdown. Now, what's ironic about this, or counterintuitive about this process, is that in order to add these phosphate groups, you actually have to expend energy to do that. Right? So this actually costs you some ATP. It costs you some energy. But what we'll see as we go through this is that you actually get that energy back, and you get more for that investment. Okay.
That's one question.
All right. So now, what happens next is that because you've raised the energy level, you can actually break it. Okay. Right. And so that breaks that molecule in half. All right. So as you know, I'm not going to emphasize too much the exact chemical structures. Right. I'll just like to say that this may be different in other classes. All right. Depends on what class you have. We're here just focused on the overall processes. Okay. Now, what happens is after you break this molecule in half, each of these half molecules can go through this process of reducing power and ATP. Now, I'm showing to you in this sort of simplified cartoon form to give you the overall understanding. We're going to go back and look at it a little more detailed chemically, just so that you have sort of a more real-world framework to put this in. But for now, we're going to stay with these little blocks. What happens here is that if we take this half molecule, we go through these steps. In one process, we make NADH, okay, and then further down, we make ATP. And we actually get 2 ATPs from this process. And in the end, what we're left with is pyruvate or pyruvic acid. Right? So pyruvate and pyruvic acid are the same thing. And again, this reflects that sort of the evolution of this class. Some books they call it pyruvate, some books they call it pyruvic acid. I think this one calls it pyruvic acid. So, but that's what this refers to. Okay. All right. So now, let's try to put this together a little more in terms of what we get out. So I'm going to go back to this board here. And now I'm going to try to add a few more pieces to this just to give you a better picture of this. So we start with glucose. Okay, we start with glucose. And one thing that your book uses which I'm going to start using, is it looks at it in terms of number of carbons. Okay. So if you look at glucose, how many carbons does it have?
6.
6, right? So we can actually write it like this.
C6, H12.
Yeah, right. So it has 6 carbons. Now, what happens is when we start going through glycolysis, okay, we're looking at glycolysis. We need 2 ATP molecules, right? In the first steps. Okay, right? And then what happens is that activates so that we can break it down now into half molecules. So how many carbons are going to be in each half?
3.
3. Okay, so, right? Now, keep in mind that I am not by nature a chemist, right? So I have to draw things very simply. So this is about all I can handle right now. Okay, so that's all you're going to see from me. All right. So now, if you take one of these, and we go through the processes here. Okay. Remember that we get NADH. So I'm just going to draw one half. You get NADH, right? In one set of steps. You get how many ATPs?
2.
2 ATPs. So now going back to the overall picture, you start with one glucose molecule. How many NADH molecules are you going to get?
2.
2, right? Because you have each half. Okay. All right. And then how many ATPs are you going to get?
2.
2 net.
2 net or 4 overall. Okay. Okay. So let's try to. I have to be careful how I word this to avoid confusing you. So what happens is that you get 4 ATPs produced. It costs you 2. Okay, so your net is actually 2 ATPs. So it's positive, right? And then plus you get 2 NADH molecules, okay? I'll do a check a little bit later on to make sure this is correct. All right, so, okay, so we get 2 ATPs and then 2 NADHs. Now, the way to think about this is, one way to think about this is, let's say you invest $2, okay? When you go through this process, you actually get back $4. All right, so that means you've gained 100%. You doubled your money, okay, which is actually really good. All right, okay, so that's what we mean here by net. Okay, so you actually double your money each time you go through this process. Remember, E. coli does this over and over and over and over again to make all the ATP that it needs. Right? So it's actually a really good process for doing that. Okay. You also get 2 NADHs, and we're going to see how this gets used later on. This actually has energy in it that can be used. Some of you know already. Okay. Now, just to finish up the accounting process, you're left with pyruvic acid. How many carbons are in pyruvic acid? 3. Okay, so there's 3. All right? All right, so that's kind of where you go with this process. Okay? All right, any questions about that? So if we look at this reaction overall, so now one thing I try to do, especially in a chapter like this, is you're going to see the same thing presented in different ways. And the reason why I do this is I'm hoping that one of those ways will make sense to you. Okay, and so what you have to do is find the way that makes sense to you, right? That helps you to remember this. Okay, so this is kind of like the overall chemistry view, where we start with these are the starting materials. So here's our glucose molecule. It has 6 carbons. We go through the entire process. We end up with 2 pyruvic acids, which you can see right here. Okay, we have a net of 2 ATPs, and we have a net of 2 NADHs. Okay, and so the important part of this, first of all, the important parts are that we get 2 pyruvic acids, and we get 2 ATPs and 2 NADHs. Okay, all right. And so that's what we get out of the process, right? So we put in glucose, we get out pyruvic acid, and we get out ATP and NADH. Okay? Now let me ask you this. Is there still energy that we can get out of that molecule? Can we still get any more energy out of the pyruvic acid? Yes, all right, because we actually still have 3 carbons here, okay, that are connected together, right? And there's other atoms that are connected to in this molecule as well. So there's actually more bonds that we could break to get energy, right? And that's the reason for some of the other processes that we're going to go into, right? Any questions about this? No, nope. I've got some other slide here. This is from so it turns out, this is just a story here. Turns out I found out that one of my students from spring was actually a jazz singer, and he was performing live, and so I caught him unsuspectingly and showed that to the rest of the class, so everyone else would know. Okay, so anyway, that was that story. Okay. Yes. All right. So now let me go back to this. So just to show you yet another way. This is the way that your book will show it. Now keep in mind that in this class, right, I'm not going to have you memorize all these steps, okay? Right, you do have, but this shows you where everything comes from, because some people actually prefer, like to think about it this way, right? But just to show you what happens. Now let me try to get this going here. I got to turn this thing turn this off. So I don't want to hear it. Where is that sound? Okay, so just to show you what happens in each process. So here is where we add the phosphate. And again, that takes energy. Okay. All right, and then now I'm going to kind of speed this up because it goes kind of slow. So now we're going to add another phosphate. All right, so that's that process there. Okay, and then what happens is we're going to split that molecule in half. So that's that process right there. Okay, right. So for those of you who actually learned all the names, this is where it fits into the simplified version that I described. Okay. And then what happens next is you're going to start getting some of the outputs from this, some of the products from this. And now there's some steps that actually go on. So as you can see, I really simplified it compared to what actually goes on. And even this is a simplified version of what actually goes on. But there's all these different steps that go in that occur. Now here is where the NADH gets made. Okay, so in this process here, all right. So you can see how that occurs. And then that sets it up also for the ATP to be made. So there's 2 phosphates that are in that molecule which allow you to make the ATP. So when you go through this, so here is where we get 1 ATP being formed. Okay, and then further down you get the other ATP formed. Right. Now in your book, they actually show you the steps, all right, so that if you want to see where all this comes from, you can look at that, right? So again, depends on what grabs you in terms of learning this, all right? And this actually occurs much faster in real life than on this animation. So let me see here. All right, so so there's our pyruvic acid at the very end. Okay? All right, any questions about this? Now, again, to emphasize for our course, right, the view that I want you to have in mind is this, right? Because this actually shows you what goes in, what comes out. So it shows you the glucose that goes in, NADH and ATP that come out, okay? And here you can see the pyruvic acid, right? As we left off, there's still energy that we can get out of those molecules, right? Out of that pyruvic acid. And that's where this part comes in, the Krebs cycle, okay? So that's what I'm going to describe next to you. All right, so here's the Krebs cycle, And and I actually just check to make sure. Did it actually? I just want to make sure that the picture of that gas unit and make it in your slides. Okay, good. All right. So I won't get incriminated. All right. So what happens is that perfect acid gets further broken down, okay, by the Krebs cycle, so that now you get carbon dioxide. So okay. Actually, I'm jumping ahead, way ahead. So first of all, before we get into the Krebs cycle, let me back up here. So you get pyruvic acid. And then what actually goes into the Krebs cycle is acetyl-CoA, okay, acetyl-CoA. That has, so how many carbons are in acetyl-CoA? There's 2, right? So some of you from chemistry, remember acetic acid has 2 carbons, is that right? I barely remember that, right? So, okay, so, and then also from this, because you have 3 carbons, you lose carbon dioxide, you get 2 carbons. That's actually what goes into the Krebs cycle. And what happens is that acetyl-CoA goes through this cycle, and from processing that 2 carbon molecule, okay, you get these products. So I backed up here and said, okay, from this pyruvic acid, you break it down into 3 carbon dioxides. Now if you think about this, in terms of our carbon accounting, that's about as far as you can go, right? So now you have 1 carbon molecule. You have a 1 carbon molecule. You also get 3 NADHs, another form of reducing power called FADH, and you get some ATP out of this. Okay? All right, so again, the NADH and the FADH2, that's the reducing power. The ATP that's produced is produced by substrate level phosphorylation. When we look at this in more detail, so here's our acetyl-CoA. It has 2 carbons. Okay. Remember, you lost one of the carbons from pyruvic acid up here somewhere by generating carbon by kicking off carbon dioxide. Right. So now you're down to 2 carbons. Those 2 carbons will now get broken down by going through this cycle. Right. So what happens here is that you see this molecule that feeds in here, this is oxaloacetic acid. It has 4 carbons. Okay. Then you get, by adding those 2 carbons, you get citric acid. Right. So the one process you actually probably do have to keep in mind is this one, citric acid, because another term for this is called the citric acid cycle. And you may see that in other classes. So that's kind of your hook to this, is that represents the first molecule that's formed when you actually go into the Krebs cycle. Okay?
Regardless of what you call it, it's still always anaerobic in this process, isn't it?
So you actually find it in, so although it itself is not an aerobic process, it's tied into the electron transport chain, and so it's often associated with aerobic processes. Okay? There are, in bacteria you can find it, and we'll talk about this. You find it associated with respiration. That's probably the easiest. That's probably the safest way to describe it. And we'll get into that a little bit. So you go through this. And again, you don't have to know the individual steps for this, okay? But you can see where all these products come from. Here's the NADH. Here's the FADH. Here's an ATP that's produced by substrate level phosphorylation. Okay. So again, one thing you want to know is what types of ATP producing processes are involved. So here it's substrate level phosphorylation. Okay? All right. All right. It gets more interesting because we'll actually talk about oxidative phosphorylation and photophosphorylation, but right now it's all substrate level phosphorylation. Okay? All right, any questions about this? All right, so that's the Krebs cycle. Okay? And so again, you can see that here. You see what goes in, you see the CoA. You can see the carbon dioxide that gets kicked off to go from pyruvic acid to the CoA. Here you go through the Krebs cycle. You go through, you lose CO2, you make some ATP, you make some NADH, you make some FADH. Okay? Right? And the beauty of this, because the reason why it's called a cycle is if you notice, if you go through this process, all right, you get to a point where you go back to where you started, and this molecule is ready to take up another acetyl-CoA to repeat the cycle again. So this is an example of a circular metabolic or cyclical metabolic pathway. Okay? All right, any questions about this? What helps to go through this is, is to sit down and try to trace through all the steps that we've talked about, right? And so that you get it kind of clear in your head about what the processes are, what you get, what goes into a process, and what comes out. Okay. All right. So one set of molecules that we haven't looked at yet, which we're gonna start covering today, and we'll get more into. Is that clock? What
Right.
is that?
Almost 2:50.
Okay, so I'm seeing, okay, so I have to make sure that I'm seeing the right time there, all right? So
2:45.
yeah. So, one process we haven't talked about yet is what happens to this reducing power. And this is where the third process comes into play, which is the electron transport chain, okay? All right, so it turns out that this reducing power that we've made all along is going to be used. Again, this is a way of storing energy. We're actually going to get that energy out in the electron transport chain. And for a cell that does respiration, this is actually very important because most of the ATP in respiration actually comes from this last process. Okay? So let's start going into this. And again, we'll go more into detail on this next week, Monday. Okay? What happens in the electron transport chain, what this process does, it captures electrons from electron carrier molecules. So we have various molecules that make up the electron transport chain, which act as electron carriers. And what they do is they capture electrons from one molecule, pass it on to another. And so it gets passed on from molecule to molecule. And in this process of getting passed from molecule to molecule to molecule, that flow of electrons is used to make ATP. So we actually get ATP out of this process. And this is where the second ATP process comes in play. It's called oxidative phosphorylation. And so this is where we get ATP being made. Okay. Now, here, what the that reducing power that we talked about, NADH, this is where it comes into play. This is where it gets used. It's used actually as a way to donate electrons to start the electron transport chain. Okay? And so it donates electrons to this process, and then those electrons get passed on from place to place, from carrier to carrier, and then ATP gets made at the end. Okay? It's actually made by this enzyme called ATP synthase that we'll get into a little bit later. So right now I'm going to try to introduce this to you, and then we'll go more into this next time. Just to give you a little more information about these carriers, these electron carriers. There's 4 types. One is called a flavor protein. Another is called a metal-containing protein, or iron-sulfur proteins. You have ubiquinones, and you have cytochromes. The reason why I bring this up is that some students, some of the health-conscious students, will recognize some of these names. Like if you go to a nutritional supplement store, you may actually see something that has this term, or cytochrome. I see that one, okay? And the thinking behind that is that it can provide some of the essential molecules to help maintain this electron transport chain, right? Because as we'll see, it's a very important energy generating process. Whether that actually happens when you take those supplements is another question, but that's kind of the thought behind this. Now, let me leave you with this thought. What happens is, this is a figure from your book. What this figure shows is what happens to the energy level of those electrons as they get passed on from carrier to carrier. So here we see electron transport chain represented in this form, where up here this is high energy, this is low energy. Okay? So as electrons get passed on from carrier to carrier, those electrons lose some of its energy. It loses some of that energy. And what happens to that energy is that energy gets used periodically to make ATP. Right? So here we see ATP made at this point, here we see ATP made at this point, here we see ATP made at this point. Until finally the electrons get dumped off because there's no more useful energy to get out of it. We get it where it gets dumped off to a final electron acceptor, okay? And that's where we end up with our final product. All right? Okay, now, one question is, when you look at respiration, aerobic respiration, what's that final electron acceptor? Where are the electrons that get dumped off at the very end? All right, so if you look at this process, what's the final electron acceptor?